Okay, so I am going to go through SN1 and SN2 reactions. So above I have like SN1 and SN2 reactions just simplified. I'm actually going to go through those as I move through this video. I think it'll be easier instead of just explaining this so you guys can see it. Okay, so we're going to just start with SN2 reaction. So an SN2 reaction is a reaction in which you have oh, actually, let's take a step back. SN, whatever SN1 or SN2, it means substrate nucleophilic, right? And that one or two has other like meanings depending on the reaction. But the substrate nucleophilic part is the part I want to focus on, right? It means that there's a substrate, right? There's some kind of molecule. Hold on, I'm circling it, but I want to do a bright color. Is pink. There is a molecule that is being like something's being done to it, right? That's the substrate, okay? And then we have another molecule called, and this is what I'm doing in orange and blue, the nucleophile, right? So if something is nucleophilic, that means it's going to want to quote unquote attack the substrate. Okay, and that's how like reactions happen, right? This nucleophile will come in and attack this substrate. And so this is very similar to how an acid-base reaction would work, right? You have, okay, let's do just the small one here. You might have an acidic species. Wow. In a basic species. Okay. And that sodium is a spectator. That OH is going to come and attack, right? Now, and so that's what I mean by the attacking, right? And so just like a base would attack an acid, a nucleophile will attack the substrate, okay? So I know there's a lot of stuff going on right now, but I'm going to explain everything. So now we've identified our substrate and our nucleophile, right? That's like, you know, how you define this thing. Okay, so let's keep talking about these things, okay? So I'm going to actually erase this thing that says nucleophile because we know this is a nucleophile, right? It's going to attack, right? Okay, so let's talk about this thing called the leaving group. Okay, so on the substrate, we have something called a leaving group. And it is what its name says. It leaves, okay? Now, in an SN2 and an SN1 reaction, the leaving group leaves a little bit differently, right? In an SN2 reaction, the leaving group leaves because it's like kicked off by the nucleophile attacking, okay? But that's an SN2 reaction. SN1 reaction, the leaving group leaves first, right? And that causes a couple things to happen, and we're going to go to that, right? But that's one of the main differences between these two reactions is what the leaving group does, right? If the leaving group leaves first, it's SN1. If it leaves as it's attacked, it's SN2. Now the question is, how do you know what's going to happen? Okay, so before I answer that question, let's talk more about the leaving group because this is important, okay? I want to break down each part of these reactions so you guys can understand the roles they play, and then we're going to get into an actual problem. Because I feel like once you understand the roles they play, then you might be less confused about why certain things do certain things, okay? So leaving group. Both of these things have trends, actually. I don't know why I erased this. I'll just say nuke for short. Nucleophile and leaving group have what's called trends, Okay, and these trends are really important, and honestly, it's honestly like a little cheat sheet you can use for your exam. And these trends are all in the periodic table. Okay, you don't have to memorize these, but it'll make your life easier. So for the leaving group, we want a big leaving group, right? So for the leaving group, bigger is better. Okay, and we want it big because we want it to be able to leave as easily as possible, right? So in SN2 reactions, right, the nucleophile is going to attack and kick off the leaving group, okay? And it would rather the leaving group get kicked off relatively easily. And that's made possible by the leaving group being bigger. The bigger it is, the more space it has. And I'm going to give an example right here. But these are the trends. Fluorine to iodine and down goes from smallest to biggest, right? And so that means that these are going to be better leaving groups because there's more space, right, between them and the carbon that's being interacted with because of the nucleophile. Okay, and there's an example right here. If you have iodine as a leaving group, iodine is very, very big. As you can see, there's a lot of space, right, between iodine and this carbon because of its size. And because of its size, this nucleophile can easily fit in here and kick off this group. Okay, so that's what's important about having a good when the book or Jermaine says good leaving group. That's what it means, or whoever's teaching your organic chemistry class. That's what it means by good leaving group. So you want a good leaving group, okay, for both reactions, right? And you want a good leaving group specifically for SN1, but we're going to talk about why, right? And a lot of that has to do with the leaving group leaving first. But, okay, so leaving group, that's what's important about leaving group. Okay, nucleophile. So the nucleophile, right, we said that it's the thing that attacks that, that connection that the leaving group has, right? So when you're trying to figure out nucleophilic strength, this is kind of a simple explanation, right? You're going to have leaving groups that, I mean, not leaving groups, you're going to have nucleophiles that aren't as simple as this, but this is just a general gist of it. And this is going to be really helpful, okay? So the nucleophilicity increases from fluorine down to iodine and from fluorine to the left over to carbon, right? And this translates to these species that down here, you know, a carbanion, this NH2 minus group, this OH minus group, these types of things, right? Because you're not just going to have just a carbon. It can't be neutral and be a good nucleophile. But these trends have more to do with the elements themselves, right, and their properties when they have these charges, okay? So we want a good nucleophile for SN2. Okay, so let's take a step back. All right. So SN2 reactions so far, we have a substrate and a nucleophile, right? Which is what these were right over here, right? Substrate, nucleophile, okay? And the substrate holds what is called our leaving group. And that leaving group is going to have a lot to do with this reaction, right? Okay, and then we have a nucleophile. The nucleophile is what's going to attack this carbon, and for SN2 specifically, kick off the leaving group. Okay, and so if you're confused, this metal, sodium, it dissociates in water or in water. And water is usually present in these reactions. So it dissociates in water, so it's a spectator. So just treat it like it's just an O with a minus. Okay. So one of the key pieces, the key important things for SN2 is that you want a strong SN2. You want a strong nucleophile. Okay. So here is that summed up. Because you want a strong nucleophile because it's going to attack first, right? And so I'm going to explain all that, right, as we break down the reaction, okay? So we have our substrate with our leaving group, our nucleophile, and And now we're going to go through our solvent. Okay, so solvent right now is not as important for at least this chapter. It will be important, but here's a couple things I want to note, right? For solvent, SN1 prefers a polar protic solvent, and we're talking about SN2. SN2 prefers polar aprotic. Okay, what's polar protic, polar aprotic? Okay, polar, we know what polar is. Protic, aprotic means that on these solvents, there's a heteroatom, oxygen, nitrogen, right? Heteroatom. And this word protic is telling us that on that heteroatom, there is a proton. In this word aprotic, a meaning without, protic meaning proton. So SN1 prefers a solvent that is polar with a proton on the heteroatom. SN2 prefers a solvent that is polar without a proton on the heteroatom. But I said preferred because SN1 can also have polar aprotic solvents. SN2 can also have polar protic solvents. So both can have either one. It just prefers one over the other. Okay? So we've talked about the pieces of this reaction. Now let's actually move through it, okay? And talk about some of this other stuff, like what's important about the substrate and all these things. Okay, so let's run the reaction. Okay, so I just turned the molecule around, but it's the same thing. Okay, let's make it easier. So, here's our steps. The first step is nucleophilic attack. Okay, so the first step, right, and remember we said our sodium dissociates because it's a spectator, right? That's why that's gone. Our first step, our ethoxide is what this is called because we have a methyl ethyl oxide, okay? Our ethoxide is going to attack the carbon bearing our leaving group, okay? So that's the first step. The leaving group gets kicked off because the nucleophile attacks, but it attacks a certain way, okay? It attacks in the way called a backside attack, all right? So in reality, it's gonna, okay, my bad. It's gonna go like around here, okay? So actually, it would have been better to draw the other way, but it doesn't matter. Okay. Actually. Okay, there it is. Backside attack. Okay. Hold on, just gonna make sure it's the same thing. Yep, there it is. Okay, awesome. Moving on. So, backside attack. And that backside attack does what's called an inversion. Hold on, we can do pink. Inversion of stereochemistry. Okay? It's only going to attack this one way for SN2. Right? And that's important because, we're going to go back. If you do the RNS configuration, 1, 2, 3, R to S, hold on, so it's going to be S. I didn't. And it should be R. 1, 2, 3, R. Okay. Yep. Okay, so the inversion is literally an inversion. The stereochemistry changes. The stereocenter flips, right? And so because it's an inversion, now I gotta erase this stuff so you guys can see this. An inversion will change the stereochemistry, which will change the way it looks in space. As in, this bromine is dashed over here. Okay, hold on, let me erase this so you guys can see it. This bromine is dashed, and when it inverts the stereochemistry, it flips to wedged, right? Because the stereochemistry is now inverted, okay? And the bromine's kicked off. Okay, so that is how SN2 reactions work. Okay, we really want a strong nucleophile, like we set up here. We want a strong nucleophile. We also, I didn't mention this, we want a substrate that is not clogged up, right? So, as in, SN2 reactions prefer substrates that are first and foremost primary, then secondary, then tertiary, as in primary, secondary, tertiary, right? Well, I'll keep that there actually. Because the first step is the nucleophilic attack, right? So you don't want stuff like getting in the way of this thing attacking. That's why you want it to be really primary or secondary, not tertiary. Because tertiary, right? Like, okay, this is gonna have a hard time coming into the backside because these things are just rotating and flipping in space, and so, and because it's only gonna do one type of attack from the back, it's not gonna work well, right? Okay. I'm going to make another video on SN1, so this one's not too long. But that's SN2. Let me go back through it one more time. Okay, let's make sure. Okay, we've covered everything. We have a substrate was covered. Right, it wants to be smaller for the nucleophile to get involved. We need a strong nucleophile, right? Because that's going to be the first step. Okay, then we want a polar aprotic solvent, and then we want it's going to have an inversion of stereochemistry, right? Also, SN2 reactions will only have one product, right? Because it's only an inversion, okay? So we got, sorry, I'm scrolling so much. Okay, so we got our leaving group, okay? Then we have our substrate, right? We have our nucleophile, okay? And the nucleophile likes to be negatively charged, by the way. It doesn't have to be. Water can be a nucleophile. Water's a weak nucleophile. Then we have our trends, all right? You can pause the video for that. We have our trends on leaving group, trends on nucleophile, right? We understand why leaving group is important, why nucleophile is important. Solvent, we explained that. Ran the reaction, right? So the first step, the nucleophile attacked from the backside, because this is SN2. Kicking off the leaving group. The leaving group was a good leaving group, right? Because it's big. And then that backside attack will invert the stereochemistry, right? And so if you actually do the RNS, it'll flip it. And there's only one product. And that is the anatomy of an SN2 reaction.